Hello, everybody. My name is Michael Kraus, and together with my colleagues Andrea Toffolon and Professor Andreas, I want to talk about the deep learning-based method for the prediction of the buckling resistance of SHS and RHS hollow sections today. Let me give a short outline of this talk. So at first we start with a motivation. I will give some background on machine and deep learning. Then we will talk shortly about the generation of the database underlying the deep learning and calibration. I conclude my talk with a short summary and an outlook. So why are we dealing with deep learning and the prediction of buckling loads here? So there is a significant increase in the use of high-strength steel, which has led to the renewed interest in the strength and stability design criteria for especially hollow sections. This is due to the fact that the majority of the resulting cross-sections and beam columns are to be classified as slender. Furthermore, most experts at the moment would agree that the state-of-the-art design formula according to the Eurocode for such cross-sections and high-strength materials combinations would be rather conservative and do not allow for utmost efficient and thus sustainable design. Before going into more detail, let's get some background on machine and deep learning. So when does it make sense to use machine or deep learning in such a setting? I think that there has to be three necessary ingredients there. One is that there has to be at least some pattern in the data for the effect we are searching for. We have data about the phenomenon, and the mathematics and theory is too complicated to capture it with a simple model. At the problem at hand, we would see that all the three ingredients are fulfilled. As we are doing the prediction of a continuous variable, we would go into the branch of machine learning, which is concerned with so-called supervised learning, as we have some inputs and some output variables. And as we are predicting a continuous variable, we would be in the branch of regression. And especially today, I want to present some results which we obtained for neural networks. And therefore, we are in what is called deep learning. So maybe one further note on the neural networks. As you can see, neural networks consist of at least three types of layers. So the first one would be the input layer, which takes the features or input, hands it over to the so-called hidden layers, which just as our brain consists of some neurons, which take the signals from the layer before, process it in some nonlinear way, and hand it over to the next layer. The third type of layer here is the so-called output layer or target layer, which consists of the variable which we want to predict in our case. So to sum up, a neural network is simply a composition of functions. And if we go to each layer would take, or neuron would take a weighted sum of the inputs from the previous layer, adds a bias term, and puts all that into a nonlinear activation function. So our database was generated based on experiments, but also finite element simulations within that HoloStab project. And this serves as the basis for the validation of advanced numerical methods using geometrically and materially nonlinear finite element method analysis with imperfections, which in the following would be abbreviated GMNAI. So in total, 104 full-scale tests on high-strength steels and mild steels on RHS and SHS and other custom-made sections with flat faces were conducted, plus further 56 full-scale tests and on HSS and mild steel, CHS, short members and beam columns were also carried out in a test facility in Munich. The test setup of all the tests were the one-hand side stub column test, as you can see here on the left-hand side, and a short member test, bending and compression forces on the right-hand side. There were done some auxiliary tests on the material itself, in terms of tensile coupon tests, but also some geometric measurements of the pre-deformed follow section geometries before doing the tests. In addition to the physical tests, there was a bunch of numerical studies conducted via this finite element method. This consisted of two stages. In the first stage, there was a so-called GMNIA mesh, which used the measured deformed or imperfect geometry before conducting the test, and the finite element mesh was calibrated such that the peak load as well as the post-buckling deformation shape was met. And then in the second step with the GMNII, there were some simplifications with regards to the modeling of imperfections, but also material loss was applied. There is a lot of details on that end, which I have no time, unfortunately, to go into detail. I would refer you to the papers of my colleague, Dr. Toffolon and Professor Taras with that respect. Now, let's take the last 5 minutes to go a bit more into detail of the machine and deep learning modeling and calibration. And let's look at the model architecture. So we have in total 23 inputs features, which consist of the description of the geometry, but also the steel grade and the loading. We have one target, which is the ultimate load amplification factor, which we want to predict given the 23 features. For the neural network architecture, I use 5 dense hidden layers with each 150 nodes. And I conducted a hyperparameter search where the activation functions ReLU and tangent superpolicus, but also a linear activation function were used. Furthermore, I use dropout regularization at rate lambda and a 5-fold cross-validation. L2 norm regularization lambda is varied in the steps of 10 to the power of -1 to the power of 10 to the -6. I chose to use 300 update epochs for the training, and I normalized features together with the targets to the interval of 0 to 1. For the split of the training, validation, and test data, I used 70 to 20 to 10. So I did some color marking here. You can see again in green the features which go into the neural network. These 5 hidden layers would be the blue ones, dropout regularization and so forth would happen within the blue ones. And finally, we want to predict the target, which is here given in yellow. So the training of different neural network models for the different activation functions and the regularization parameters is evaluated using the mean squared error loss or E2 loss, together with mean correlation factor B, which you can see here on the right-hand side, and the coefficient of variation of the deltas of the errors, which is the distance between predictions and finite element analysis values. An exemplary evaluation of the regularized MSE loss is given here on the left-hand side for the case of a DNN, and L2 regularization scaled by a factor of lambda 10 to the power of -5. We noted that, interestingly, the dropout strategy did not improve the training, and hence its application and results are not considered here in the further of that study. If you look at the right-hand side, you will see that all models have very good prediction capabilities on average, as reflected in a mean correlation factor of B equals to 1. However, the prediction certainty varies within the choice of the activation functions as well as the regularization value, as the coefficient of variation of the errors is a measure of the spread of the DNN-based predictions, different from the finite element simulation results. So this furthermore implies that the model with the greater coefficient of variation of data error results in a greater partial safety factor here to the left-hand side. So for that reason, we chose the model with the smallest coefficient of variation. And with that, we go further and investigated the determination of the design value of a resistance model given by that DNN. And we wanted to come up with a partial safety factor in accordance with the Annex D of Eurocode 0. And I think this is the first time anybody did an analysis of a partial safety factor with an artificial intelligence algorithm. The computations of that partial safety factor show that the obtained deep neural network serves very well as a surrogate for the estimation of characteristic buckling loads of RHS and SHS steel profiles, and thus gives rise to a partial safety factor of gamma m is equal to 1.0, which is very nice. Finally, let me point to some efficiency analysis. So here on the left-hand side, you can see the results of the design of all the columns with respect to the current status quo of the Eurocode 3. Here you can see a big scatter and design results, a lot of overestimating the material. With the generalized slenderness-based resistance method, you can see an improving of that over design over all cross-section classes. But finally, and in the end, the neural network is really capable of predicting the true buckling load to a very high accuracy. Okay, let's come to the summary and outlook. We conducted a total of approximately 20,000 data points consisting of experimental and numerical investigations on the buckling loads of RHS and SHS hollow sections. Based on that, we calibrated several neural networks, investigated the performance of the neural networks by tuning the hyperparameters, and finally found a partial safety factor of 1.0. I could show that our deep neural network-based prediction improves the performance in a significant amount. Therefore, we could provide improved design by efficiency and sustainability by deep learning methods. In the future, the use of explainable AI methods is intended in order to investigate more the contributions and importance of features in more detail. And we want to understand the embedding of the features into the mechanical formula in more detail. Finally, further studies on deriving a neural network-induced design formula will be used in order to come up with a Eurocode-compatible format of the design in the future. Having said all that, I want to point your interest to the available literature on that topic. Please contact me or Professor Taras. We are happy to discuss further points with you or answer some further questions. Stay safe. Bye-bye from my side.